right, so question 3 is a little bit of a break for us because it actually talks about functions and sets. So this is actually pretty easy. Oh, sorry, way too big. Yeah, that just is good. So, what's question 3? Well, let F be a mapping from two sets, from E to F, between two sets, not from two sets, sorry. From E to F. And actually, these look incredibly ugly, so I'll just write normal E and F. So let F be this mapping from E to F, alright? So then, let A and B be two subsets of F. So that this, which is F inverse of A intersect B, is equal to F inverse of A intersect F inverse of B. Now, while this might seem intimidating because of the equal sign, both proofs are actually incredibly short. So let's first go the first direction and say X is in F minus 1 of A intersect B. Now we need to show it lies in the other set. So how do we do that? Well, if X is in F inverse of A intersect B, that means F of X is in A intersect B, which means that F of X was in A and F of X was in B. So what does that mean? That means X is in F inverse of A and X was in F inverse of B, which means that X was in their intersection, F inverse of A intersect F inverse of B. Now for the sufficient proof, we say X is in F inverse of A intersect F inverse of B. So what do we get? We get that X was in F inverse of A and X was in F inverse of B, and from there we mostly replicate the logic backwards to get F of X was in A, F of X was in B, which means that F of X was in A intersect B, which means that X was in F inverse of A intersect B. Alright, so that's the necessary and sufficient proofs showing that these two sets are equal.